Welcome back for another episode. We're going to continue with the components for Tinkercad, and we're still doing resistance, and we're still playing with the meters. Now keep in mind, if you were using a real meter, like the ones behind me, I'll grab one. If you were using a real meter like this, you would be constantly moving the leads between different points in this circuit. And you would have alligator clips on the end here, and you would have to clip it. Well, when you look at what we're going to do, at one point we'll have 6 meters on the circuit. Well, in real life, you would move the meter around and write down your measurements. But what we're going to do is we're just going to put a bunch of meters in the circuit and then talk about it. It's actually easier to understand if you have many meters. And then later on in this episode, I'll get into something that's more advanced. Keep in mind that what I'm doing is I'm trying to go through the basics, but I'm trying to do a complete mind dump on everything I know about electronics and electricity from a practical aspect. I'm staying away from the math as best I can. I mean, I got A's in calculus in college, A's in chemistry. So it's not that I don't know the math, but you don't need to know the math to do electricity and electronics. You need to know some Ohm's law at a minimum, and we do talk about Ohm's law. So let's jump in and see to this. Tinkercad components. We're still dealing with resistors, and we may do a little bit more with that switch. That slide switch is a single pole double throw, and basically what that means is I'll start the simulation, and of course there's nothing to observe because there's no lights, there's nothing. And right now this circuit is on. In other words, we're on right here. So you can turn the battery pack, the 6-volt battery pack, 4 batteries, 1.5 volts each, that's 6 volts. You can turn it on and off there, and you can turn the circuit on and off here. So now the circuit is turned off. You have an open. A single pole means that you have a single common, and then you can throw it to this pin or you can throw it to that pin. Right now, the center pin is connected to this pin, but nothing's connected to that pin. So we're really not using it as a single pole double throw. We're using it as a single pole single throw. It does something there, it does nothing there. So single throw. Okay, so we're simulating, but there's nothing to see. If the circuit's doing something functional, you can't see it. You don't have any meters, you don't have any lights, no motors running. We just have 3 resistors. Stop the simulation and we'll talk about our circuit. You have a battery pack, and remember there are basically 3 ways to create an electrical charge. The first one discovered was static electricity. It was created by friction. Remember that all matter, solids, whatever, are made up of millions, billions of atoms, and each atom has a number of electrons. And the electrons in the outer ring, because remember there are orbits, inner orbits, orbits in the middle, and then ones that are further out. The orbits that are further out, those electrons aren't quite as tightly bound to the nucleus as the ones that are closer to the nucleus. Certain materials, if you rub them together, we call that friction, you can generate static electricity. And there are static electricity generators that you can go on YouTube and just type in static generator, and you can see designs for doing something, building something that continually rubs materials together and gives you a continuous source of electrical charge based on friction. That was the first one discovered. The second one discovered was chemical. They discovered, and in all cases it involves, 2 different materials. The static, remember the triboelectric series, that was in an earlier lecture in the Electricity with Grandpa series, that we had a whole list of materials, and the higher up on the list, the more positive, the lower on the list, the more negative, which means the one furthest down on the list is going to be the one that gets electrons pulled off of it by friction. Then we go to two dissimilar materials again, but this time more in the area of metals. And we dip it in an acid, and the two metals react differently. In the case of a standard dry cell, like the little AA, AAAs, C cells, D cells, the chemical is a paste, a caustic paste, and then you have zinc and you have carbon. And there's an immediate chemical reaction that builds up electrons on one side, meaning that it leaves atoms missing electrons on the other side. There's your voltage, your electrical pressure. And then, of course, you can use kinetic energy to force a conductor through a magnetic field, or force a magnetic field through a stationary conductor, and you can generate electricity. What you see in front of you is chemical. There are 4 AA cells there that make a battery, a 6-volt battery of 1.5 cells. The black terminal marked negative, the red terminal marked positive, waiting at that negative terminal, because it's hooked to the negative end of that group of batteries. There are free electrons just waiting there to go somewhere. And then on the red terminal, it's attached to the positive end, a bunch of atoms that are missing 1 electron each, and they desperately want that electron back. If you provide any path, any conductive path from the minus to the plus, the plus charge actually expands out into the wires, the negative charge expands out into the wires, and wherever they meet, then you start getting current flow. Within that current flow, we have 4 devices. I'll start the simulation again just so I can turn this off. This switch right now is turned off, which means that this is an open circuit right there. There is no electrical connection between that terminal and that terminal. There's an infinite amount of resistance to current flow right here at this switch. When I close the switch, and now I have a piece of metal going from here to here, a conductor, now there is basically 0 resistance, or for all practical purposes, 0. Remember, I showed you in the last episode that all metals, and I showed you a chart for copper and how many ohms of resistance per 1,000 foot. So you might as well say that these green conductors, they don't have 0 resistance, but it's so low it's negligible. We just consider it 0. The switch has 0 resistance, and all the green wires do. So that means right now electrons are racing from this terminal through this circuit back to this terminal. But in order to get through there, the pressure, the 6 volts of electrical pressure generated here chemically, is being used to push electrons through this 500 ohm resistor and this one, and then this one. These are all 500 ohm resistors. Now, the way I've got them in there, I normally put the bands, I would have this resistor flipped around. I just noticed that it doesn't have my usual left to right, but that's fine. Green for 5, black for 0, and then 1 for 1, 0. So 5, 0, and 1, 0, 500 ohms. Okay, these 3 resistors add in series. It would, like, remember when I explained about straws in a milkshake? If you took, we'll call it a 500 ohm straw. I mean, you don't measure the resistance to sucking up milkshake through a straw in ohms, but let's pretend. If you put a 500 ohm resistor in your milkshake and you put some suction on it, you get a certain amount of flow. If you put 2 of them in parallel, in other words, side by side, and you got both of them with one end in your mouth, the other 2 ends in your milkshake, and you provide the same amount of suction, you're going to get basically double the flow. But let's say that instead of putting them in parallel, you attach them end to end. So you took a 12-inch straw, 2 of them, and you connected them end to end. In other words, you connected the one on the end of the other, maybe put a piece of tape on it to make it good and solid. And now you have a 24-inch straw. when you put the same amount of suction on it, you're only going to get half the volume of flow that you would have gotten if it was just one 12-inch straw. Here we have three 500 ohm straws in series. We have a 3-foot long straw that you're trying to suck milkshake. And remember, this is sucking, this is the suction in and this is the supply in. You dip the straw down in here and you're trying to suck milkshake out of this with 3 straws in series. Or you could just say that we have 500 plus 500 plus 500. Now we've got 1,500 ohms, 1,500 ohms of resistance. Now this is called a voltage divider because the only reason you would do this is if you wanted to divide up this 6 volts. Right here, you got 6 volts between this terminal and this terminal. The switch is closed, there's no voltage here. It's all divided up between these 3 resistance. Pretend like this was a hose, a water hose, or a tube, water tube, and this was a pump, and the whole thing was full of water. You have water flowing through this tube and back to this reservoir pump. And let's say that the resistors weren't there. It was just clear tube. You're going to get a certain amount of flow. If I put my fingers right here and pinch right there, it's going to reduce the flow. If I keep 2 fingers right here pinching the tube right there, not pinching it off, just pinching it a little, that's going to reduce the flow. If I then take my other hand and come over here on the tube and I put the same amount of pinch here as I did here, now you're going to get even less flow. That means more resistance. And then I call you over and say, hey, bud, put your fingers here and pinch this guy just a certain amount. All 3 of these oppositions to the water flow add. They're cumulative. The resistance accumulates, which means with each one, the flow went down. The greater the resistance, the less the flow, because the voltage stays the same. The 6 volts stay the same. Now let's quantify that a little bit. I'm going to drag this down and have a modified. I'll bring this over. And what I've done is I've added a current meter. Now remember, if you're going to measure flow, you have to put the flow meter right in the flow. All the flow has to go through the flow meter. So we took the meter and we hooked the black lead to the resistor. And just for grins, I don't think I can do this. Nope, I have to stop the simulation, make that one black and make that one red. Okay, I could do it that way to make it look more realistic, because if you had an actual multimeter, you would have the black lead hooked right there and the red lead hooked here. We'll leave it that way for now. Now we have 5 devices in our circuit. We have the switch, 3 resistors of equal resistance, and then we have a meter. Now the meter was put in there to measure the flow, not to interfere with it. But we all know from experience that if you insert any kind of device in that circuit, it's going to affect the circuit. With that thought in mind, we'll start the simulation again, and you see you've got 4 milliamps. Okay? And we have 6 volts and 4 milliamps. If I go over here and look at Ohm's law, I know the current and I know the voltage. I've got 4 milliamps, 3.99 milliamps, and I have 6 volts. If I bring up a calculator and I divide 6 by 0.00399, that would be 3.99 milliamps. Remember, we have to shift the decimal place for 1,000. Milli is 1,000ths. This is a decimal fraction, and what was displayed here, the M is the same as 3 decimal places this way. Because remember, the meter doesn't have enough display to show 0.00399. There's just not enough space in there on a real meter. Okay? I do the calculation right here, 6 divided by 3.99 milliamps. and I get 1,503, well, I rounded off. If you know how to do your round off, the 9 makes this a 6, and the 6 makes this an 8. You've got 1,503.8 ohms of resistance. Now I'm going to stop the simulation, and I'm going to remind you that these are 500 ohms each. Where's this other 3.6, if you want to call it that, or 3.8, I'm sorry, 1,503.8. Where's this additional 3.8 ohms of resistance coming in? Well, you could say it could be in the switch, it could be in the meter, it could be in the battery. Well, we already know from a previous episode that when you cause current, you allow current to flow through the battery. Remember, it's got to flow through these in series. The electrons come in on the plus side, they go through one battery, then the other, then the other, then the other, and back out. You got 3 AA's in series, which means the total combined resistance, internal resistance of this battery pack and that meter is 3.76 ohms. Now, to further exemplify that, let's enhance our circuit here a little bit more. Of course, we're going to need some more space, or I'm going to have to make it smaller. First, I'll try just making it smaller, leaving enough edge here so I can get to these two. And we'll drag her over. It looks like we can get it all in there. That's good. Now, all that we did, and I could still make this conductor black and this one red. I'm not sure I want to do that because the green represents our circuit. Okay, and our circuit that we're really concerned about are these 3 resistors, not the switch and not these meters. The reason I have 2 meters here, this one is the amp meter, see A for amperage and V for volts. I want to measure if there's any voltage lost across this meter and if there's any lost across that switch and what's across these resistors. I'm going to start the simulation. I'm going to turn this switch off. And now, how much voltage is there across those 5 devices? You got a switch, 3 resistors, and a meter. Well, there's no voltage there because the resistance right here across this open switch is infinite. There is 0 current flow. There is no voltage felt, no pressure felt across these points of resistance. That would be like you've got your hose pinched with your fingers in 3 places and a little tiny pinch here if you like, and you turn the spigot off on the outside of your house or your valve totally off. It has infinite resistance to water flow. You've got no flow, therefore there's no pressure felt on these points of opposition. Now we'll close the switch. Watch what happens to the 6 volts. Now, without the ammeter in here, you would expect those 6 volts to be divided up pressure-wise across these 3 pinch points. And notice that it is. Now, the one thing that I find perplexing is that it shows no voltage dropped across the milliamp meter, although I know there's some. The problem is it's so small that that meter is not sensitive enough to measure it. When you look at multimeters, if you go online and you look at a multimeter, it will give you something called impedance. And in the amperage mode, to measure amperage, when current flow flows in this black terminal and out the red terminal, it goes through an impedance in here that impedes the path of the current flow. Otherwise, it wouldn't be able to measure. So literally, what they've got inside this meter between the red and the black lead, they have a fixed resistor that is so low in resistance that you can barely measure it with a meter. Remember when we did the copper wire, and for the wire that was a 1/2 inch in diameter, for all intents and purposes, the resistance of a piece of that half-inch wire an inch long would be 0. You couldn't measure it. That's what it's called, a shunt. There's a shunt resistor inside of this meter, and so there is a little tiny bit of millivolts or microvolts being consumed right here to generate a value for this meter to display. It's actually measuring a milli or microvolt, and then it's doing a calculation because that shunt resistor is a known value of ohms. It looks at the voltage, and it does a calculation. Okay, the voltage coming in from the current flow tells you how much current flow. The resistance is known, calculates the current, and it displays it. But I don't need this meter on here because it isn't doing anything of value. So I'm going to stop the simulation, and I'm going to remove it. And notice remove the wires too. Now I'm going to start the simulation up again, and you see really nothing has changed. If we've got 6 volts, it's showing, 2 volts across here, each of these, but it's not 1.99. It's not reflecting the voltage lost across the internal resistance of these batteries, but I know it's there. I'm just telling you that this is really not 2 volts, but they're equal. Whatever they are all equal. It's 1.9999, 1.9, 1.999, something like that. We're dealing with the practical aspects of electricity in these circuits that we're doing. And I'm showing you how to work with the components. Now let's see if I've got one more. I don't think I do. Let's go up here a little higher. Nope. This is the workspace for Tinkercad. And if I turn the switch off, what do you expect these things to read here? What do you expect these meters? This one reads 0. 2 volts plus 2 volts plus 2 volts is 6 volts. Okay, now, this is a voltage divider. I have divided up the 6 volts into 2 volts, 2 volts, and 2 volts. And you do that with resistance. Now, if I click on this one and double the resistance, what do you expect to happen in the rest of this circuit? I'm going to double this one and leave these two the same. If all 3 of these are equal, if I double this one, won't it equal the sum of these two? 500 plus 500, I make that 1,000. Wouldn't you expect the voltage across these two to be equal what's across here? And it's still going to add up to 6 volts. But because I increased the total resistance from 1,500 to 2,000 ohms, what would you expect the meter to do? I can type in 1,000, or I can be more clever, and I could go to K ohms to get you used to that idea, and then put in 1. Okay? This is 1,000 ohms, or 1 K ohms. We normally don't say 1,000 ohms, we say 1 K ohm, meaning kilo, 1,000. Whichever you like, you can do it any way you want because this is Tinkercad. This isn't the real world. In the real world, you would be using a 1K resistor. You can say it's 1,000 ohms, and everybody will understand what you're saying. Now, this resistor right here, brown, black, that's 1, 0. Red is 2, that means 2 zeros. So 1, 0, and 2 zeros, 1,000 ohms. 5, 0, and 1, 0, 500 ohms. Notice that the voltage drop across this resistor is equal to these two combined. This is 1,000 ohms. These are each 500. 500 plus 500 is 1,000. These two together are equal to that resistor as far as opposition to current flow goes. Now, I've gone a long ways, well over 20 minutes. I'm going to have to cut this short and then pick this up in another video. So I'm going to pause for a second and see if there's anything else that I could show. Well, I have an idea. Just as if you flip the switch off, all the voltage is here, 6 volts, 0 here, because this is infinite. The resistance is so high, there's no current flow here. But let's say that the current flow was so low that you might not be able to measure it. So I'm going to go here, and I'm going to go from 1,000 ohms to 1 million ohms. Now look what you got. You still got current flow. I promise you, this switch is still on. You've got 3.03 millivolts. You've got 3 thousandths of a volt across each of these. And for all intents and purposes, you might as well say the whole 6 volts is across this guy. Let's go one step further, really increase the opposition, and go to gigaohms. Now look, does that not look like there is all the voltage is across that 1 gigaohm resistor? And if I turn off, it shows no current, but there is current. It's just too small for this meter to measure it. If I turn off the switch, where's the 6 volts going to go? Okay, I stopped right there because what happened next kind of took me by surprise. Remember that this is all a computer simulation. And credit to Autodesk that they're making it as realistic as they are. What happens next, like I said, it took me by surprise because at first I thought I broke the software. In other words, I bumped into a bug. But rather than just assuming it was a bug, I started thinking about the real meters, the real devices, and so then I enter into a explanation and discussion that you wouldn't get in a basic electricity class. When you go into the rest of this episode, if you feel lost, just stop and go back and watch the first part again to make sure that your head is tidy and everything's in its right place. But it was a really interesting situation. I'll probably find more of this as I get deeper and deeper into going over the components and discussing basic electricity. Let's look at this next section, which at first took me by surprise. Over there. Now that is interesting. I broke it, is what I did. I just broke Tinkercad. That should read 0. There's no current flow. See, no current flow. So how's it measuring 2.87 volts across there? I literally broke it. So I'm going to put it back to 1 meg to see if it fixes it. It didn't. Isn't that amazing? So I'm going to turn this back on, back off. The only thing I can think of is that maybe they're trying to demonstrate picking up stray RF electromagnetic energy out of the atmosphere like an antenna. I'm not buying that. I think I broke Tinkercad. This should read 0. If you did this in real life, you had real resistors in there and you had a 1 meg. So I'm going to turn it on. I'm going to turn it off. I'm going to stop the simulation and start it again. Amazing. So I don't know whether to delete this or leave this in here. But you know what? You're liable to run into this stuff using Tinkercad. So I would be interested in what Autodesk's explanation is. Now I'm going to take, if I turn that on, off I mean, that's off. So this, unless they're allowing current flow through the meter, the voltmeter. I hadn't thought of that. So this is the only explanation I can think of is when we run this resistance up real high, let's go back up to 1 gigaohm. No, see, when I go up to 1 gigaohm, now it's splitting it between these two. So it is considering the impedance of that meter. That's the only way I can explain this. Remember I explained to you that in order to measure a voltage, whether it's here or these, you have to have current flow through the meter. Not to power the meter. The meter has a battery in it or it's plugged into the wall. But in order for this to measure the voltage, it has to have current flow, which means that this is not infinite resistance. These 4 meters, they're voltmeters, they are not infinite resistance. So even though this switch is off, this conductor through the meter makes a complete path in a sense. Not in a practical sense, but in a theoretical sense. So just to go a little bit further with this, I'm going to make these also giga-ohms. And we'll make this one 500 as well, so they're both the same. Okay, so look, it's basically dividing up this 6 volts into 4, for all intents and purposes, equal. And I can't increase this one. In other words, I can't increase the resistance here internally, the impedance. But I could decrease these until I got closer to this. So hang in there with me. I know I'm doing something that is unusual, so I'm going to decrease these to 400. Giga-ohms. This is totally out of the box, folks. So if you're new to this, I hope this isn't confusing you. Look, I can't quite get it exactly. I could keep lowering the resistance until there was more current flow, so this would show a higher voltage. But I'm just going to leave it there because I've already introduced something I never intended on introducing. But I'm going to leave it in here. I'm going to leave the explanation in here. And if this is what Autodesk has done with Tinkercad, that they're considering the internal impedance of this meter to complete this circuit, even though the switch is off, kudos to them. Very insightful. Okay, we're stopping right there. Went way too long. I just couldn't help myself. I left in that discovery. I wasn't expecting their simulation to be that realistic. And I hope you understand that when you put a meter in a circuit, there is current flowing through the leads of that meter. Otherwise, you wouldn't be able to read anything. So that voltmeter completed the circuit to the rest of the circuit. And the only reason that we even noticed it was because we bumped the total resistance way up there. So we actually were dividing up the voltage across the meter. It's not really across the switch because it's the impedance of the meter in parallel with the open switch is what we were dealing with. So I hope you enjoyed it. Have a good day.